Hello, this is a brief video tutorial showing you how to use the tracker application to measure the frequency and period of a pendulum near the surface of the Earth, allowing us to calculate the gravitational acceleration constant. I have several pendulum videos that I have pre-recorded and measured the length of, and this is an 83.7 centimeter long pendulum. So we will start by selecting our starting frame by dragging the little black triangle at the bottom down, and selecting our ending frame a couple of periods of this pendulum swing after the initial one. So here is 1 period, and 2 periods, and 3 periods. Let's go back to the starting frame and create the coordinate axes. So this defines our 0, 0 point. I'll put that where the pendulum is attached. Then I'm going to hide that because it's kind of annoying to have up. I'm going to create a calibration stick. I know the distance from the inside of these pieces of red tape is 100 centimeters apart, or I will use SI units and put this 1 meter apart. Now I can also measure the distance from where the pendulum is attached to the center of mass by using the tracker functionality. I can right click on this video, select track, new, measuring tools, and tape measure. And I can measure anything in this video. In this case, is about 87.2 centimeters, which is close to what I measured when I took the video. But I'm going to delete that and just use what I measured beforehand. So now I will create a point mass to start auto tracking. I can zoom in with the mouse wheel, and I can pan around by just left clicking and dragging around to get a little bit more of an accurate position of the center of mass. And now for the auto tracker keyframe, I'm going to press Control Shift and then click on the very center of that. I can also increase the size of the frame that the auto tracker interface looks for. That looks good. And then I'm going to search for it. This may take a few moments, but you can see that the sinusoid in the horizontal dimension is evolving. We can see 1 period. And there's 2 periods. And that should be enough for what we want to do. So I'm just going to go ahead and stop this video, or stop the auto tracking, and then focus our attention on the analysis of this plot. You can also get the other plot. This is in the Y dimension. You can see that this is actually 2 times the frequency because the Y dimension hits a maximum at 2 different points in one swing. But what we really want is the horizontal frequency. So I'm going to right click on this plot and go to Analyze. Let's make this bigger. Click on Analyze again, and go to Curve Fits. Now the curve fit brings up a plot of this function in a magenta line. We don't want just a y equals mx plus b line, we want a sinusoid. And the auto fit doesn't always work, but that time it actually did. You can see that the magenta line actually matches very well with this data. But if you need to manually go through and find this, why don't I just turn the auto fit off? It's still there. But I'm just going to set this at some random amount so we can manually find this frequency. So the first thing, there are three parameters here, A, B, and C, and they should be labeled amplitude, angular frequency, and initial phase. The angular frequency is the one that we're really interested in, but those correspond to parameters in this equation. So A times sine of B times t plus C, all within that sine function. The A is the amplitude, or the distance from 0 to this peak. B is the angular frequency, or how often this crosses 0. And C is the initial phase, which just shifts the whole waveform left and right. So I'm going to try and adjust these parameters to fit this plot. So I'm going to start with the amplitude and just increase that until it's about right. You can see that this is about 0.17, so you can also just put in 0.17. Maybe a little bit bigger than that, so I'm going to increase that. You can also adjust the degree to which you increase or decrease something by clicking on this 10%. Let's just adjust it by 1%. And maybe that looks about right. Now I'm going to adjust the phase, so that's going to shift this whole waveform to the left until it matches relatively well. And now I'm going to adjust the frequency, this B parameter, until the frequency matches up. And so that magenta line looks like it is coinciding with our data pretty well. So again, the important figure of merit here is the B parameter. Ignore that negative sign. This is 3.41 radians per second. I'm going to switch over to Excel now to enter that. 3.41. I already have my length in there. And now I can proceed to find G and the other variables of interest here. So the frequency is equal to omega divided by 2 pi, or the angular frequency divided by 2 pi. So I'll say equals that divided by 2 times pi. The period is just 1 over the frequency, so this is equal to 1 divided by d4. And then G is equal to 4 times pi squared times the length divided by the period squared. And there you have it. That is a number that is close to the given value of 9.8 meters per second squared. I hope you learned something. Goodbye.